Good morning, everyone. True Zero Emissions here. So I'm thinking about battery charging right now, and I know we talked earlier about, is there such thing as battery charging, or is space charging batteries by sending a signal to the battery that rings the battery like a bell, right? And the bell, the batteries, the plates, shake the electrons loose from space, from the Dirac sea holes, right? From the Dirac holes. Or from, I'll just say, just study Dirac holes, right? So, and then what is heat then? So why does quick charging cause heat sometimes, right? Depending on what we're talking about, right? Are we talking about gbatteries.com, where the batteries do not heat up? And I imagine with that kind of charging system, right, they're talking about low resistance, right? Do you think you would be reading an amp? Do you think you could put a meter on that charger and read amperage? What do you think would happen if you read amperage from the charger to the battery? Amperage is, we can say that that's really the obsolete way of charging a battery, right? We don't want amperage. We don't want current. We don't want, well, let me say that differently. We don't want amperage. We don't want resistance, right? Because resistance causes heat. Now I'm going to share something interesting with you that I was learning about the difference between a high voltage system and a lower voltage system. So we all understand how, if this scooter was, for example, let's say this scooter was a 12 volt battery powering the wheels, right? It could still be a big battery, right? So it'd have lots of what we think of as amperage, right? Amp hours? Yeah. But it would have the capacity to push a lot of amps, right? Only 12 volts though. So if this scooter was 12 volts, it's actually a 72 volt system nominal, which is 84 volts fully charged. But if it was 12 volts, would it be as fast as it is now? Because right now it goes 70 miles an hour, right? This scooter will go 70. This is the Wolf King GTR. Well, I don't think it would go 70, and I think everything would run hot. I think there would be we would need a lot of current, a lot of amperage. We would need, look what I just said, we need a lot of amperage. That sounds like I'm saying we would need a lot of resistance. So what is voltage? Why does voltage have the potential, the limitless potential, to do so much work so efficiently, right? And why does higher voltage allow for less resistance? I'm going to say it that way because that's the way I perceive it. That's the way I experience it. So I was thinking, there's two sides to this. On one side, we're using high voltage to power a scooter, right? So we have a high-powered battery, high-voltage battery, running this scooter very efficiently. And I would like to see the scooter with even higher voltage. What if this was a, we can go a little higher. What if we can go 100 volts, right? So fully charged would be like 105 volts or 94 volts, right? What if we can get closer to 100 volts? I think that would be amazing. And I think that would be a good direction to go. But if you notice, the best scooters are all going higher and higher in voltage, right? If you look at, like, for example, the Dualtron Thunder, which I'm not a fan of the front suspension on the Dualtron Thunder, but other than that, other than the front suspension down here, other than that, because I prefer this kind, this is more stable. This is a stable suspension when you have the two bars. But other than the Dualtron Thunder's front suspension, if we look at the rest of the scooter, that's a very high quality scooter, and they used to have 60 volt batteries, right? So fully charged was 66 volts, 66.4, 66.5, 66.6. We call it 66 volts, right? They went up to 72 volt system, which fully charges 84 volts, same as this. The scooter is faster, it's more efficient, and there's less resistance. This is my own perception that I'm sharing. I'm sharing my interpretation of what I've studied and experienced, okay? So now that's on one side. On one side we have using high voltage to cause motion, right? Now what if we use, similarly, if we say on the flip side of that same coin, that might be one way of saying it, but similarly, right, because now we're using the energy, right, to move We were using the stored energy to move the vehicle, the scooter. I'm just going to say it that way because actually it's a little bit different than that, but I'm just going to say it that way for the moment. The other way is using high voltage, high potential to charge the batteries. And it's something that I haven't seen in a battery charger. Like when you look at battery chargers, they stop right at where the battery is. How do I say this? So let's say this is an 84 volt battery, right? Let's go back to our 12 volt battery. Then we'll come to this. I'm going to try to use a similar analogy. So earlier we were talking about if this was a 12 volt battery, it would require a lot of current, a lot of amps, a lot of resistance. It's strange to say it that way, to say it would require a lot of resistance. Maybe the proper way to say it is that we would see a lot of resistance in trying to make the scooter go fast with only a 12 volt system, right? But if it was a very big 12 volt battery, it would have the capacity to make the scooter go pretty fast, right? I think we could do it with the right gearing and everything, but there would be a lot of resistance, right? Because the voltage is so low. So the wires would heat up, the battery would probably heat up, the motors would probably heat up, everything would get hot, nothing would be happy, right? We certainly wouldn't be happy because we want efficiency, right? So if we want efficiency, the higher, to me, from what I'm seeing, the higher voltage we go, the better. What if we can make a 400 volt system? Notice electric cars are hundreds of volts. I think they have like 400 volt systems in them, right? So I don't see why not making a scooter like a 400 volt system and then just turning the power down, like electronically. You just turn down the power, but it would have the ability to go faster than anyone would want to go, and that it would be even safe to go. So that would have to be locked where it couldn't. It would have to cap the speed, right? I mean, there's the Ryan scooters. The Ryan scooters can go. There's some of those scooters that can go over 100 miles per hour. I don't think everyone does it, but I think some people have probably tried it on the safe conditions. Safe conditions would have to be an absolutely flat track. So, okay, so going back to our analogies here. So if we have a 12 volt battery and we're trying to make a scooter go very, very fast, there's going to be a lot of current, a lot of heat, a lot of resistance, right? Of that energy in the battery trying to make it to the controller, trying to make it to the motors. Okay, so we know now, we've established the idea that higher voltage allows greater efficiency of achieving higher speeds and allowing everything to stay cool, right? I mean, things can still heat up if we're pushing it really, really hard, but let's just say it this way, to achieve the same speed of the scooter. So whatever that speed is, whether it be 20 miles an hour, whether it be 100 miles, well, let's say 40 miles per hour, or 70 miles per hour, or 80 miles per hour, we could have different tests, right? Where we try the 12 volt battery, and then we try the high voltage battery. We could just say the 84 volt battery that's in there now, which is a 72 volt nominal, 84 volts fully charged. So at the same speed, we would have less heat, less waste heat, less greater efficiency. Just really is one way of saying it. Greater efficiency, greater delivery of the potential, right? The voltage, greater ability of the voltage to do work without being wasted making heat, because we don't want to make heat, right? That's what's strange about the automobiles that we use. If we're still using the they're popular being called water cars now. Toyota's calling them water cars. If you're going to call a car a water car, then we can't ignore that gasoline's water, because it is. It's mostly water. That's what hydrogen and oxygen is. That's water. So it's water with carbon, right? So Toyota's making this water engine, but water engines are highly inefficient. What I mean is the combustion engine is highly inefficient. Okay, I've seen numbers as low as 11% efficiency. That would 11% efficiency means 89% of the energy in the fuel, the water fuel energy, whether it be water or gasoline. It doesn't matter which one it is. It could be water without carbon, or it could be water with carbon, which is called gasoline or petrol. And then we have we still have, if we're using the combustion engine, which is a highly inefficient design, right? The combustion engine, no matter what you do to it, no matter how you change the valves and the pistons and just all the things that are being done, porting and polishing and the cams and the special timing and everything, variable timing, all these things that could be done. The engine, it's still a combustion engine, it's still a heat engine, and it's still putting, I think the Department, I don't know if it was the Department of Energy, I think it was the Department of Energy, but government agencies research this themselves, right? Themselves research this. If I understand correctly, I believe it was a Department of Energy paper I read on the internet, and if it was a real one, which I've researched this in many different ways, and it did appear to be real, but my whole life I've heard this from engineers. So even if that paper on the internet was not correct, it's still a fact that remains true, that combustion engines, even if it's a Prius or a hybrid, the combustion engine part of that system, right? The electric motor might be in the 90% efficiencies, right? 90+% efficiency, even 98% efficient possibly. But the gasoline part, the water engine part, the water plus carbon part, the petrol gasoline part, is putting between 11% of the energy in the liquid, I'll just call it a liquid fuel. The liquid fuel is being converted into kinetic energy, which moves the automobile, at an efficiency of approximately 11% up to 40% max. Not more than 40%. So that means 60% of the energy in a combustion engine, it doesn't matter if you're running it on water or if you're running it on water plus carbon, which is gasoline, petrol, it's still only putting, if I understand correctly, it's still only putting 40% or less of the energy in the liquid fuel to moving the automobile. That's why electric is better than a water engine, So advertising can be fun and everything, but we can't ignore. There was a professor, a USC professor, that was talking to me. He said you can't ignore the numbers, and I think he's correct in that, because you can't ignore the fact that no matter what fuel you put in the engine, you're still, by the way, this was a retired USC professor that was talking to me about this. He was an engineer his whole life. He was an engineer for NASA, and he made a lot of things for experimental things that he was proud not to talk about. I said, that's fine. I don't need, I always tell people, don't tell me any secrets. I don't want to know anything I'm not supposed to know. I enjoy learning things on my own, and I always find what I'm looking for, because that's the nature of the universe. It'll show you what you are looking for. If you're looking to understand something, you'll find it. And they say to set your mind to it. That's it. You'll figure it out. Now, people may not agree with you. They might have trouble relating to you. But look, they had trouble relating to the airplane, and until everybody started building one. And even today, if you don't relate to it, you can still use one to get around. And that's how I feel. Even if I don't understand how the battery charging works, or I have theories on how it may work at low resistance battery charging, so quick charging with increasing cycle life, with low resistance battery charging, if it works, I'm happy. That's, if I could charge my scooter in a minute, 5 minutes, 10 minutes, 20 minutes to 100%, or, I think it'd be fun to charge it in a minute or two if it wouldn't get hot. That would be nice, right? So G batteries and many others have achieved 10-minute fast charging of batteries, whether it be electric cars or scooters. G batteries charge the Xiaomi M365 scooter. That's on their YouTube channel, and they charged it in 10 minutes. And they use the low resistance charging. Okay, so going back to that, I'm going to go back to that example I was talking about earlier, the two sides of a coin, right? So we talked about high voltage being very efficient for powering a scooter, right, or powering an electric car. Now I'm thinking, when it comes to charging batteries, it seems that we use something called constant current, constant charge, constant voltage, or constant current, constant charge. I'm not sure. I think it's constant charge, constant voltage. I have to look it up, but that can be easily looked up. It's CC CV, I think. CC//CV. But we're basically I feel like we're just pushing the energy really hard, right? Causing a lot of resistance, right? So it's like that continuous energy, like a continuous force versus a pulsing, right? Now let's think about how the universe works, right? If we study particle physics and we know that the universe, how does it work? It works because all the material universe, including space-time itself, including the zero-point field, including vacuum of energy throughout space-time and non-space-time, and the soon-to-be created universe, right? Because the universe is always creating itself. It's charged at a rate of, let me think, 10 to the 120th, if I recall correctly, 10 to the 120th times per second. That's how many pulses it is. Now, I don't know what does that look like? So we put a 1 with 120 zeros, and then I don't know what that number is called, but that's how many times per second in a unit of time, in a 1 second, in a human second, I'll call it. That's how many times the material universe is pulsed and maintained its charge, right? So the charges that let this material be what it is, all the material universe, right, is being sustained by the 0-point field. If I understand correctly, 0-point field can be called many things, right? It can be called vacuum energy. It could be called the 0-point field. It can be called, I think it's also called like dark energy, or like there's so many names for things, but we have different names for things that we don't know what they are, and then we try to define what they can do and what they are, right? Like I was talking with someone once, and they were saying, not just one person, okay, I say this sometimes, and then someone will say, well, that was me, what are you talking about? Well, there's always more than one person that says this, so I'm not like trying to point one person out, and I'm not using any names. But I was talking with someone about the 0-point field, and they said, oh, well, the 0-point field is great, it has lots of energy, but we can't use it. And I'm like, well, every step I take, I'm using the energy. How am I not using it? When I take a step on the ground, the space, the material universe pushes back with an equal and opposite force that I push upon it, right? Where does the material universe that I just took a step on, where does it get the energy from to sustain that pressure, to push back, right? Because every action has an equal and opposite reaction. Well, it gets it from the 0-point field. So how is that not using the energy? And our circuits, right? Our circuits, is the power station making electricity? No, they're pumping it from the environment. The environment that I'm talking about is the 0-point field. That's the very space that the wires that come to the homes exist within. It's the very space that surrounds the wires, right? And it's the very space throughout all of space, okay? With or without time, right? Because there's both time and non-time. There's like simultaneously time, because we say there's time, and it's a way of us thinking about things. But also there's no time. Fundamentally, there's no time, really. So, we can make up something called time and say, well, we need it to make things work, to make the math work, right? So we invented this thing called time to make the math work, But it's just a tool. We're trying to make up these tools to help us see and imagine, right? So going back to the battery, similarly, on the flip side of the same coin of using high voltage and being very efficient, which allows low resistance, allows less resistance when we're to go fast, right? And less heat build up because there's less resistance, less current as well, right? Similarly, if we charge a battery with high voltage, with the higher the voltage that we use, the higher voltage we use, and then rather than continuously charging, what if we used intermittent charging, right? You can call them pulses, we can call them different things, but let's just say intermittent charging, where then on, off, on, off, on, off. Now, is there one way to do that, right? Because there's lots of people that have done this in the past, and then there's people all over the internet going, it's been done, those were all scams, that's all frauds, that's not true, you can't do that, it's been proven. Well, guess what? Flying was proven to not work until the one day that it did work, because no one gave up. People didn't give up on it, right? So I don't know who the first person was to fly. We talk about the Wright brothers because that's what was taught in school, the Wright brothers. But now there's all these other people that were flying. There's so many people that were said to be the first one to fly, but it's not about getting lost in the names and the meanings of the words necessarily, as it is the idea of what we're talking about is that things move, they transition from impossibility to possibility, and then to achievement, right? To be among the collection of infinite achievements that we've achieved so far as a humanitarian planet, right? That's what we aspire to be. I think Earth is aspiring to be absolute humanity, which is like no more fighting, no more war, and finding ways to work solutions out, which has to be emphasized in school right from the beginning. And it's something that parents also have to. We all have to learn that, right? I'm not a parent yet, but I'm just saying, like, it's something that adults need to learn, because we all teach one another, right? So if we think about high voltage battery charging, isn't it interesting that chargers never go beyond the voltage of the battery, right? It just goes right up to it. And then it charges, it seems like, in this one way where it just pressures the battery, it pushes this energy in it really hard, right? And then it just does it the whole time, right? So then you get the charger getting really super hot, we have the wires getting warm, we have the battery getting warm. Now, if we compare that to another approach, what if we use super high voltage? What if we use double the voltage? Now, when I say that, that does not mean overcharging the battery. What I mean is just using high voltage to get the battery up to a fully charged state. So we're still going for 84 volts. If this battery, which it is, 84 volts fully charged, then I don't want to exceed that. I don't want to go past that. But can I use high voltage, and how high a voltage can I use before it gets to the full capacity, right? And then how do I measure what's going in the battery? Well, if we're using low resistance charging, we might need different tools. We might have to create different tools that can measure pulses, because if a pulse sends current before voltage, then when does the resistance show up? Maybe it's possible that when the voltage shows up, when it bumps up on the meter, maybe that's when resistance would show up. But we want to disconnect the charge. We interrupt the charge before resistance shows up, right? One of my thoughts were that G batteries. What if what G batteries is doing, and I'm hypothesizing, what if what they're doing, because it sounds so complicated, like artificial intelligence based algorithms. I'm reading this going, oh my gosh, I feel like I'm reading this journals from the future, and I don't know how to relate to it. It sounds very complicated. But then I think about Donald Lee Smith when he used to write his patents, and he said that he was, it almost sounded like he was intentionally trying to make what he was describing very complex. And a lot of people know, if not everyone, that something that is terribly complicated and terribly complex becomes infinitely simple once understood. Now, something can be simple to the person, but that doesn't mean we know how to explain it. That can still be complex. But that's part of the work, though, right? Part of the work is, how do we use simple words and simple concepts? Some people call them big concepts, right? Like the big picture. How do we use these simple ideas? How do we translate complex ideas into simple explanations, right? That still contain all the important information of what's taking place, right? So with battery charging, one of my thoughts are, so high voltage, right? Using high voltage and using the interruption, right? The charge, and then disconnecting the charge, and the charging, and then disconnecting the charge. And doing that, right? So we have current being pulsed, because the current comes at the current gets delivered before the voltage, right? So we're hitting the battery, right? We're ringing it like a bell. It's being charged from space itself, right? Which is the way I think all batteries are charged. It's just that the question is, what's the most efficient way to do it, right? That's the question. And whatever we think is most efficient, let me ask you this as a rhetorical question, do you think G batteries is charging batteries at the absolute fastest a battery can be charged? I don't think so. I think they've done great work. I think that what they're doing and what they achieved is very important. But since we're always improving, and since nature itself is the great teacher, and because nature charges instantaneously throughout all space and time, everywhere, right? So like when I power a light bulb, the entire universe contributes to the powering of that light bulb. The energy that we require to exist, right? Our bodies are interacting with the 0-point field at all times, right? And the energy that we require to exist is powered by the entire universe. We're instantaneously connected throughout all time and space and all non-time and non-space, right? Our bodies are. And that includes everything. And that includes our circuits as well. So if nature is the great teacher, then what can we learn from nature, right? So we have these things, what people talk about sometimes in high-level collaborations is that they have heated debates, or people are screaming at each other and their faces are turning red and everybody wants to do things their way. But my question would be, how can we work together in a collaborative way, in a way that is of the greatest efficiency, right? Because we all want the same thing. We want safety, right? We want efficiency. So we want infinite safety, right? Infinite safety. We want infinite efficiency, which is like the absolute best efficiency we can get. We want that. And we want life, right? Which for the human body would be Aubrey de Grey's work. Aubrey de Grey, reversing aging, right? And for our circuits, it would be efficiency to begin, and I'm talking about very elementary introduction ideas here, is with the circuits, to begin, it means no less than 100% efficiency. No less than 100% efficiency, no less. Because if we're below 100, which it's almost like electrodynamics, if electrodynamics could be defined as the theory that our circuits are described, our circuits, if our circuits are claiming that we cannot have a more efficient circuit, if circuits could make that claim, circuits don't make that claim, people make that claim, right? People say, no, you can't do anything else. But if we're taught a philosophy of relating to a circuit and told that's the only way we can relate to it, well, that doesn't really make sense, because the way it actually works is we can be taught how to relate to a circuit as an elementary beginner, kind of like a predictable way, like this is how we repair a circuit, this is how it works. But certainly we know from the universe being the great teacher, from nature itself being the great teacher, we know that there's other ways to relate to everything, including circuits. So now if we just look at the 0-point field and the material universe, this is an example of greater than 100% efficiency, because the 0-point field contains 10 to the 40th times more energy, magnitudes more, right? 40 times more, 10 to the 40th times more. That's a 1 with 40 zeros, and there's that much more energy in the 0-point field, which is just space. That's just this, what we think of as empty space, but there is no such thing as empty space. But you can just say this space, right? Space everywhere, right here. That has a 1 with 40 zeros. That number, whatever that number is called, it could be looked up on Google. 1 with 40 zeros, what's the name of that number? That's how much more energy there is in the 0-point field than there is in the material universe. And the 0-point field entirely sustains the material universe, 100%. All the energy that allows my hand not to slide right through this bag, right? Just fall right through it. Everything that we see is pure energy, right? If you want to know how much energy it takes to create matter, E equals mc squared. That's the amount of energy that it requires to create matter, okay? So that's what the 0-point field does, right? Because the 0-point field creates the material universe, right? So creates and sustains the material universe. Now, how exactly it does that, that's something I'm still learning about. But definitely interesting to me, right? How could it not be interesting, right? We're interested in creation. We're talking about creation here. I mean, that's the way I perceive it. So now what sustains the 0-point field? How does the 0-point field get its energy, right? That's a natural question to ask. Who charged the 0-point field up? What's the power station for the 0-point field? Are you ready for this? The material universe. Talk about perpetual motion. The material universe, which is pure energy, right, powers the 0-point field. And the 0-point field powers the material universe. And it just goes back and forth at 10 to the 120th times per second, which is a 1 with 120 zeros. That's the name of the number. That's how fast it does it. So let's talk again about pulsing a battery, about charging a battery. How fast can we charge that battery? How many pulses? How fast can our circuits go, right? If we look in like radio frequencies, we have megahertz and gigahertz and these really fast cycles per second. But are we even close to what nature does? I think we can replicate nature because we're made of nature. We are nature. In fact, that's all we can do. We can't do anything but replicate nature. That's why I think we're always drawn to understanding more, right? I think that's part of it. So here's a question. This could be another video, and it will be more videos, but here's something I'm thinking about. So we have high voltage. Now let's say we're generating high voltage, if I say it that way, right? Because actually, are we generating high voltage? Is that what we do? Do we generate high voltage? I don't know. I have to think about what words most accurately describe what seems to be taking place, right? And that may change as I come to see more and more over time. But for now, we can say generating. I'll say that for now, for lack of better words at the moment. If we're generating high voltage and we're using very little magnets and very little copper wire to make that high voltage, right? Very little magnets and very little copper wire. And I'm spinning these somehow, one past the other past the one, or both of them in counter rotating directions, right? So the magnets are spinning this way and the copper coils are spinning this way, right? Something like that. Somehow these are moving past one another to let me read on a meter, right? On a multimeter, right? That I can read a voltage, right? Now, if I have this voltage, what can I do? What's the difference between what I can do with a little bit of copper wire and a little bit of magnet and a voltage? Let's say to this battery, right? This is a 2,500 watt hour, or it might be like a 2,400 watt hour to be exact, but to be closer to exact. But it's close to 2,500 watt hour. I'm just going to estimate it at 2,500 watt hour for the moment. Using my little bit of magnet and my little bit of copper and sending that high voltage. Let's say I have, let's say I can make 1,000 volts. Let's say I can make 1,000 volts by spinning the copper and the magnets past one another very fast. And usually it's the copper sitting still and the magnets passing the copper really fast. A car alternator has the magnetic field in the middle, but it's using copper wires to make that magnetic field, so it's called an electromagnet. But some people take those out. They take the copper wire out and put magnets in there, and then just spin the magnets, right? That way you don't have to put energy into the alternator to make it give you those magnetic fields, right? But in that case, in the alternator, we have a magnetic field, whether it be electromagnet or just permanent magnets or rare earth magnets or whatever they are, some kind of magnets that's spinning past copper coils on the outside, right? And those copper coils are wound around ferrous iron metal, meaning magnets will stick to it, right? Magnets interact with that metal, which means that when the magnet goes past the metal, the iron becomes polarized. It becomes a plus or a minus, and that keeps switching as the magnets go past the ferrous iron metal. So what we have in alternators, we have a switching back and forth of positive, negative, positive, negative, positive, negative. We have alternating current. But we can send that into a full wave bridge rectifier, which costs a couple dollars, and it has 2 inlets and 2 outlets. So I send the signal in with 2 wires, and then coming out is DC, but it's going to be pulsing DC, right? I can use that to charge a battery. So let's go back to my example of having a little bit of copper and a little bit of magnet and getting a high voltage and charging that battery and seeing what it does. Now, right now, at the moment, I'm going to talk about using the same battery that we're powering the circuit with that we're drawing the energy from, if I say it that way, I'm just going to say it that way for the moment. Say we're drawing the energy from the battery, and then and then that same battery to be charging it while I'm drawing the energy from it. Now, a lot of people will say, oh no, never do that. Never try to charge the same battery you're using. It's so much less efficient. And some people say it's 10 times less efficient to do that. So in other words, it's 10 times more efficient if I have a separate battery and I connect my magnet and coil that I'm spinning, right? I'm spinning a magnet and a coil. Like, well, let's say I have a wheel that touches the ground, and then when it spins, it's generating 1,000 volts, right? From this little bit of copper and a little bit of magnet, and it's spinning fast enough to give me high voltage. And I'm sending that voltage into a separate battery, not one that's powering the scooter, right? A separate battery that needs to be charged, though. Let's say it's the same voltage and the same capacity as this one. It's the same exact battery, but it needs to be charged, right? We'll say it's all the way drained to 0%, right? So now it's supposed to be 10 times easier or faster to charge that battery, 10 times more efficient than if I try to charge the battery that's being used to power the circuit, okay? So now, but I also know that people that are very, very knowledgeable, I'll say it that way, know how to charge a battery that is powering the circuit. But I always say it requires more knowledge, and it requires more wisdom and more experience too, I think. And it can be done. But for a beginner, an absolute beginner like myself, like I'm like not even at beginner stage yet. I'm like before beginner, right? And just, thinking that way, by the way, if it's not obvious, allows me the most space to continue learning. If I walk around going, I know so much, look what I know, how much do I have room to learn? I think I know it all already. And then I'm going to walk around telling everybody that they're wrong because they're saying things that don't match what I know, right? So then I walk around telling people that they're wrong, or just listening to them and not believing what they're saying. I mean, that to me, that is a very uncreative place to be in. To me, the most creative place to be in terms of a state of mind is what leaves me the most space to learn, to be open to learning, to be open to collaborating, to making something new that we haven't seen before, right? But with the universe, we've seen it all. Anything's possible. Anything is inevitable, right? So going back to the experiment, we have a separate battery, we'll say next to the scooter. It could be mounted under the scooter, but the wires are only connected to the charger. When this wheel spins that we add to the scooter, this is just I'm just doing a thought experiment right now. We have this added wheel that rolls on the ground, and when it spins, it generates 1,000 volts. Now, how does that little bit of copper and little bit of magnet making 1,000 volts going to the battery at 1,000 volts, how does that charge the big battery, the 84 volt battery, right? How does it charge it? Does it charge it? Does the charge change at all? Would it take days to charge, right? Now, what if I now increase the copper, the amount of copper I use? And these are different things that could be done, right? I'm thinking for myself. This is all experiments I would like to do. And now I'm doing them as thought experiments, right? I don't know if I'll actually do them, if I'll create them, but I feel a need to kind of walk through this process and kind of write this down in my journal, which is what I'm doing right now. This is my journal. My YouTube channel is my journal, okay? And it's a thought experiment, just like my life is. My life's a thought experiment. And if we have a lot more copper, and now there's two different ways this could be done. One way is really thin, lots and lots of thin copper wire, right? And I think thin copper, if I recall correctly, makes higher voltage. So if we have lots of thin wire, really thin wire, but lots of it, like really big coils of it, and then we have really powerful neodymium rare earth magnets, right? And then we're making the same voltage. We're making 1,000 volts with that. And how do I arrange the copper coils and the magnets? How do I arrange them? Do I have them continuous copper all the way around and then continuous magnets? Or do I have the copper like here, right, like here, and then here on this side, right, 180 degrees over, So I have copper coil here and here, and then I have two magnets, one here and one here. And let me think about this. I'm guessing I would want one magnet to be south facing out and one magnet north to be facing out. So when it passes those two coils, which are connected to one another on one side, and then the other side of the coils are connected to the full wave bridge rectifier, and then that goes to the battery, right? Now, why would I want it to pulse like that, to pulse instead of continuous? Well, because continuous creates a lot of resistance, right? This is just what my research and study indicate this. If we have continuous coils and continuous magnets, and then we're charging a battery with that, that's going to create heat. That's going to create what people think of as reducing the cycle life of the battery, right? But if we have these pulses, the opposite happens, right? Because now we're replicating nature, right? I mean, we're moving more in the direction of what nature's doing. Nature uses pulses, right? 10 to the 120th per second. That's a big number. I've read it before. I don't have it memorized, though. It's a big word. Something else happens now. We've reduced the resistance, I think, right? We're still delivering current. Every pulse delivers a lot of current, right? Can we measure that current? I don't think the meter would have even time to respond to that. But if it's spinning fast enough, it might show a current on the wire, but I don't know if that would be representative of what's actually taking place inside the battery, because now we're ringing the battery like a bell, right? And the battery, is shaking electrons loose from space. And remember, all space is interconnected. All the energy we could ever need is in every part of space. Like the area within my hand, right here, the area inside my hand, even though it's closed, right? Just the space between my two fingers right here, the space between my two fingers, it has all access to all the energy in the universe, because every part of space is connected to every part of space, and also every part of non-space, right? So it's also connected to every part of non-space, right? So now, okay, I'm thinking this through. Now we have these pulses, right? We still have 1,000 volts. What's the battery doing right now? I would be interested to know this. What's the battery doing? How fast is it charging? Is it charging? Now we're putting 1,000 volts into that battery, DC, right? But it's pulsing, right? I don't know what kind of wave it is. I don't know a lot about waves right now. I've read about them, but I don't know I don't understand it yet. And it takes me a long time to learn something new. And the only way I learn is by reading many, like all of them, the different perspectives, interpretations of something. I cannot read one book and go, I get it, I got it now. That doesn't happen. I have to read like hundreds of books or thousands of books, talk to hundreds of people, do lots of experiments, and then I might have a glimpse of what I think I'm thinking about, okay? So it's like the opposite when someone goes, I know everything because I have a degree, right? I don't think that's how it works, but if someone believes they know everything, to me that just means they're happy with what they know, and I'm happy for them if they're happy. But I certainly don't want people telling me not to do what I'm doing, because only I know what makes me happy, and what makes me happy is to learn, right? And we have the right, it's in the Constitution, which is that's what defines this country, that we have the right to pursue happiness, right? And I pursue happiness wholeheartedly. And part of my happiness is to share my journal with you, which is my YouTube channel. That's my journal. So let me think about this. So we're charging the battery 1,000 volts now. So we have more copper, and we have more magnet now, right? And we have, these magnets are big, right? They're big, strong magnets and big rolls of copper. And the copper test can be done two different ways. One way is the copper can be wound around ferrous iron metal, and the other way is the copper can be wound around plastic or something where there's no metal inside there. I don't know what the difference would be. That's another test that could be done, though, right? Gerard Morin, in some of his videos, Gerard Morin talked about not using ferrous iron metal and just using coils without metal, right? But then you see other great masters using a ferrous iron metal. But these are all different experiments, and they're all different ways of achieving the same thing, right? They're all different ways of achieving learning. So it's not like that person's right and that person's wrong, but it's more like, what were they talking about and how does that work? And what were these people talking about and how does that work? And what does it mean? And what's the difference between the two different perspectives and different knowledge, right? These are things that could be discussed. Even with ourselves, we're just having just an introspective conversation with ourselves. We're just reflecting on things that we think about. Okay, everyone, so that's my thoughts so far. I'm excited to share this with you. I'm really glad that I was able to explain to you at least a glimpse of what I'm thinking about. I'm doing my best to be thorough in what I'm explaining, but all I can do is just begin to share what I'm trying to think about and interested in learning more about, and I'm doing my best to do that. I hope you have a great day. We'll see you soon in the next video. Bye, everyone.